Thank you, Dr. Patrick, and good afternoon, everybody. Today, my presentation is about the waste heat power generation for the cement plants. I'll be covering this in two parts. Initially, a brief introduction about our company, and then the main topic of the presentation. And this business is being handled by the company Anhui Konch Kawasaki, in short ACK. This is based in China, in Anhui province in Wuhu city. This was established in the year 2006, and its main business is waste heat power generation, municipal waste treatment plant, and apart from this, power plant and cement plant also. And as I said, this company ACK is a joint venture company between two parent companies. One is Kawaski Heavy Industries Japan, and the other one is Konch Cement China. The parent company Kawaski, it was established in 1896, and its main business is shipbuilding, rolling stock, aerospace, motorcycle, robots, and industrial plants and power plants, and of course other sectors also. And the other parent company, which is Anhui Konch Group, this is basically a world number 3 cement manufacturer, and apart from this, they are world number 1 profiles manufacturer. So this is established in the year 1996. And we formed a joint venture to establish this new company for the waste heat power plant business. And the company location of this ACK is in China. It's around 400 kilometers from Shanghai. And this is some of the company photographs. Okay, now let's come to the main topic of today's presentation, the waste heat recovery power generation plant for the cement plants. And here you can see a typical cement plant. Along with the waste heat power plant also. Basically, the exhaust gases from two sources. That's one is the preheater, and the other one is the air quenching cooler. It's being utilized, and steam is generated, which is further fed into the steam turbine to generate power. So this is how this waste heat is being utilized. And this is the cycle which we use. It's a typical Rankine cycle, which we normally use in any power plant, coal-based power plant. This will be basically a superheated Rankine cycle. Like you can see here, the gases are fed into the AQC boiler and the PH boiler, which is then further superheated steam is fed into the turbine to generate the power. By this, actually, we can able to recover around 20 to 30% of the energy being used in cement plant. So it depends many factors, like if it's an older technology, then the exhaust temperature of the cement plant will be little higher. So you can actually recover more power. But if it's a greenfield technology of the cement plant, then the exhaust temperature will not be much high. So in that case, your power generation will not be much high, but still it's a considerable amount of power. And this slide, you can see the development of the waste heat boilers. Actually, it started in 1950s for the cement plant wet type. And then later in 1980s, the cement plant of dry type, which is of today's technology, this we started developing, but it actually gets commercialized around in 2000, which it took around 25 years for us to get into a larger scale of commercialization. And some of the components, the major subsystems you can see here is the waste heat boiler, which are 2 boilers, which I'll be covering in the later slides. And then another major component is the steam turbine and generator. Then water treatment system, which is again for raw water as well as the wastewater. Then water cooling system, it can be air cooling system also, but again, as you know, that water availability is not so high nowadays. So most of the plants nowadays choose for air cooling system. But if water is not a problem, then definitely that can be chosen, because the efficiency will go again some few percentage points higher. And electrical connection systems again, and then DCS control systems. These are the main subcomponents of this power plant. And I'll be covering this one by one in the next coming slides. First, the PH boiler. Actually, this is a horizontal boiler, which is a vertical tubing arrangement. Whereas you can see in air quenching cooler boiler, we use a different type. That's a vertical boiler with a horizontal tubing. And the reason why we use the 2 different types of boilers in the same power plant, I'll explain in the next slides. And this is some of the other major components, which is the turbine generator building, turbine and generator, then cooling tower, and the condensers and digital control systems. Sorry. And The technology. Actually, the horizontal pH boiler, as I said, it's a two different type of boilers. The first is the horizontal preheater boiler with the hammering system. And the second one is the vertical air quenching cooler with the pre-duster. And we use a flasher system because there will be a fluctuation in the exhaust gas temperature, which will be again very frequent in the cement plant. So to avoid that, we use this flasher system. And again, a reliable DCS system, which is a very important aspect for the smooth operation. So these components give you the stable and continuous power generation. And one of the other most important aspect is there should be no influence to the existing cement plant. There should not be any impact on the cement manufacturing. The power generation is to be additional recovery. It should not create any hurdle for the cement manufacturing, which is already going on. And other important aspect we need to look on is easy operation and maintenance, which I said this plant actually uses the Rankine cycle, which is more common in any power plant. So the operation and maintenance will not be a big issue in this case. And this all actually has been proven with the 30 years of experience and supply, which we can see later. And this is the pH boiler arrangement you can see here. It is actually a horizontal boiler with a vertical tubing arrangement, which has a hammering system. Actually, this hammering system is used to take out the dust which settles, because the preheater exhaust gas, that actually has a very sticky gas condition. So normally what happens if you don't have such a system of hammering, the dust sticks to the tubes, which actually will lead to heat transfer reduction over a period of time. So effective removal of this sticky dust is a very important aspect, which must be taken care, and it's one of the very critical system in this power plant, we can say. So this hammering system, if there is a heavy force we use, then normally what happens, the tubes may break. But if you use a less force, then again the dust will not get removed, and within a short duration of time, your heat transfer will reduce, and ultimately your power generation will be much lesser than what actually you designed. So that has to be taken care. So that is why it may seem very simple, this hammering system, but this is a very critical design. And you can see here the difference that why we use the two different type of boilers. The horizontal type, you can see on the left hand side, it's almost with no dust content because of the hammering system. There is no dust content and the tube is almost cleaner. But on the right hand side, you can see the vertical gas flow, which is a vertical boiler. You can see a lot of dust buildup. And in this case, actually, even if over a period of time, actually the heat transfer will be reducing, which you have to stop the plant, or again you have to make some cleaning arrangement to make again the heat transfer efficient. And this is the other boiler, which is the vertical type, of course. And this one, this AQC gas, actually it's completely different from the preheater gas, exhaust gas conditions. This gas normally has a very coarse dust particles. So actually what happens with the huge velocity and huge volume, it can puncture the tubes very easily because of the coarse particles. So here we should have again a dust removal mechanism, which a pre-duster is being used, so that the velocity of the gas, when it comes and it strikes on the plates, the coarse particles automatically gets settled down, and you get the cleaner gas, comparatively much cleaner gas in the boiler, by where you can save the boiler tubes. Sorry. And this actually also, again the design also is a bigger aspect. Like the draft class loss should not be high, because if you have a high draft class, that will ultimately lead to the ID fan replacement. The pressure drop in the ID fan will be high. If it is high, then the replacement of ID fan has to be considered, because that is not an easy affair, and it's a very costly affair to replace the ID fan in a cement plant. So basically we need to consider with both the boilers, the exhaust gas, the draft class should be very minimum, so that the existing ID fan within the margin, they can continue using it, and thereby saving a lot of cost without replacing the fan. And the another system, the major system, is the flasher. As I said, this is majorly used for the purpose of to get adapted to the fluctuation of the exhaust gas. So thereby actually we can maintain almost a constant power output. And the DCS system, as I said, this actually can be of any supplier DCS, the hardware, like ABB, Siemens, Saryakugawa, or any hardware. Because basically the programming is being done in-house. So It can be used any manufacturer, and it can be integrated with the existing cement plant, so that the operation will be much easier for their power plant operation. Yeah. And here you can see the reference till date, and total around 224 sets has been supplied till date, for totaling 319 cement kilns. And out of this, 189 sets are under operation and 35 sets are under construction. The total power generation capacity till date we achieved by this waste heat power generation is 2,469 megawatt, and it's spread over 10 countries. Majorly in Japan, where we introduced first, it has 13 plants, and then next, where now we are handling this business through our joint venture subsidiary company in China. In China, we supplied the maximum number of plants, which is 193 plants. And as I said, it's in the last less than 10 years, because 2006 we started this joint venture, and in less than 10 years we achieved this 193 plants. And in Germany, 1 plant, and if you come to India, it's 2 plants. The first Indian plant is, of course, supplied by Kawaski, which I'll cover in the coming slides. And in Germany, again, 1, and some other countries also. And this is the first plant in the world, the first waste heat power plant in the world, in Japan. This is a Tahio cement, and its capacity is 11,600 ton per day, which is of 2 kilns of 4,000 and 7,600. The total power output is 15 megawatt, and this is in operation since 1982. And till date, actually, there has been no major maintenance has been done, except only once the superheater tubes were changed. And that's also not because of any maintenance issue, it's because of the change in fuel conditions. So actually, that was the reason we changed the superheater tubes. But apart from that, it's still operating at the rated power of 15 megawatt, and there is no degradation of power for the last 32 years, I can say. And this is the first plant in China. This is in operation since 1998, which is almost for more than 15 years. And the rated capacity is 6.5 megawatt. And here you can see the operational statistics for the 15 years, starting from 1999 to 2013. And you can see the design value for the total output is around 4,087, but actual output is getting 5,448, which is almost much higher than the design value. And again, the capacity also, it's designed for 6.5 megawatt, but actual generation is around 6.9 megawatt. So, and again, the availability, 94% design value versus actual of 97.58. And the output per ton clinker also, you get about 10% higher output per kilowatt per ton. This is one of the plant in Vietnam. This is in operation for the last 12 years. It's a relatively smaller capacity of 3 megawatt. And this is a plant which I was mentioning. This is the first WHR installed in India. Not only by Kawasaki, but overall in the industry, this is the first plant, WHR plant in India. And the power output design value is 7.7 megawatt, and it's operational since the last 11 years, from 2004. And this is the statistics for this. If you see the design value and the actual generation, you can see the availability, it's around 98% versus the 94% design of availability. It's almost 98% and 99%, except 1 year it's 96 in the middle. And yeah, and this is the design value of 7.7, but actual generation is being 8.7 or 8.8 megawatt, being it's almost constant for the past 10 years. And this is the first plant in Germany. This is again in operation for the last 12 years. And this is the world's largest WHR plant, is at a single location. It's around 67 megawatt of waste heat power plant. Again, this is of 6 kiln in total, combined with 3 turbines. And this is also operation for the last 12 years, more than 12 years. And this is a new plant which is coming up in India. This capacity is 4.73 megawatt, and for 5,000 tons per day kiln capacity. This is under construction, and probably from this June, this plant will be starting its operation. I hope, and the performance, you can see the real performance, which is for 30 years, more than 30 years for the first plant at Tahio Cement, which I shown before. And the continuous output of more than 97%, which is again, we have proven this in more than one plant. There is a 15 years operation record at the first Chinese plant, and 10 years operation, more than 10 years operation in India. And I think today this is my presentation here. And thank you. If you have any doubts, you can please let me ask.